This video is talking about counting methods and methods to find out how many arrangements we can make, how many possibilities we can have. And there's 4 that we're going to talk about. We'll see how far we get in 10 minutes. The first is repeated events. The second is arrangements of various items, such as wardrobe or how many options you can have at a restaurant. The third one is permutations. This is how many possible ways you can arrange people in a photograph. And the last one is combinations, where order doesn't matter when you're doing arrangements. So let's take a look at something that's happening multiple times, saying how many options do you have if you flip a coin twice? Some things, if it's the same thing happening more than one time, you just multiply. You can draw a tree diagram to understand this, or you can draw boxes. So if you're looking at how many outcomes if you flip a coin twice, or if you flip 2 coins at once, you're going to assume one hits the ground a millisecond before the other. So the first outcome has 2 possibilities. And then if you got heads and you flip it again, you have 2 possible outcomes either way. So if we're going to write that out as a sample space, we've got our 4 possibilities. Now, the other way to do this is I just call it possibility boxes. So the first event has 2 possible outcomes. The second event has 2 possible outcomes for a total of 4. Sample space is nice because you can visualize the whole thing, but the boxes are faster. All right, so here's the next question. How many possible ways can you have an outcome if you flip a coin and roll a die? So we're going to assume, just for the sake of our diagram, that one happens before the other. It doesn't matter which one happens before the other. This works even if it's at the same time. So we can say, with our tree diagram, that I am flipping the die, or rolling the die first. I have 6 possible outcomes there. And then regardless of my outcome, I have 2 outcomes that I can have when I flip the coin. So a total of 12 possibilities. I can get a 1 heads, 1 tails, 2 heads, 2 tails, etc. The tree diagrams take a while, but they make it really clear what's going on. The boxes are faster. The first event has 6 possible outcomes. The second event has 2. We multiply them, and we get 12 possible outcomes. If they're simultaneously happening, we just pretend one happens first to visualize it a millisecond before the second one. All right, so that's simultaneous or the same thing happening. Now, if you have arranging items, it's not the same thing that's happening. You have different things that are happening, but we're going to assume one happens first. So let's say Jane has 3 shirts, 2 pairs of pants, and 3 hats. How many arrangements can you make? We're going to make a tree diagram. She's got shirts, 3 choices. We're not going to go into detail. We don't know what they are. But for pants, she's got 2 choices. And for hats, she's got 2 choices. So a total of 12 possible arrangements. And if we just do our event boxes, we'd say there's 3 possibilities for the first event, 2 for the second, 2 for the third, and so, let me go back, that's 12. All right, now permutations. Permutations are written like this as a formula. You would have 5 items, and you're choosing 2. You could have 5 items and you're choosing 5. So let's do an example here. Sam has 4 friends. How many ways can he arrange them for a picture? And we can use the formula. We can also use event boxes to predict this. So choice 1 for the picture, he's got 4 possibilities. But then he's picked somebody, so he's only got 3 choices for the second person in the picture, etc. We're going to multiply them, and we get 24 possible arrangements. When you multiply 4 times 3 times 2 times 1, a number times the number less than it, times the number less than that, it's called a factorial. So if you had 5 factorial, it would be 5 times 4 times 3 times 2 times 1. And just a side note, if you have 0 factorial, we'd call it 1. So if you have 0 factorial on the bottom, it's still 1 because we're not going to have any undefined number of choices here when we're arranging. So they've just stated that. All right, so now Sam only wants 2 friends in the picture. how does this change our story? It's easiest to do the event boxes and permutations, but we can also use the formula. So let's try it both ways. All right, so first the formula, 4p2. That's 4 factorial, and then not just 2 factorial, we need to do 4 minus 2 factorial. Whatever the second number is, we put it on the bottom, subtract it from the first number. So it's 4 times 3 times 2 times 1 over 2 times 1, which is 12. If we did it with the boxes, we'd say, all right, for the first choice, he has 4 friends. For the second choice, he has 3 friends. He's not going to do the 2 and the 1 like we did in the last example because he only wants 2 friends in the picture now. Now for combinations. All right, combinations, what if order doesn't matter? What if Sam has 5 friends and he wants 2 in a picture, but he doesn't care what order they're in? We have to use a different formula. The combination formula is when order doesn't matter. So here, Sam would say, I've got 5 friends, I'm choosing 2. And our formula for this is slightly different. It's just like the permutations formula, but there's another number on the bottom. And we'll show you why in just a second, but let's just use this equation first. So we've got 5 factorial, 2 factorial, and then 5 minus 2 factorial. So we'll write it out. 5 times 4 times 3 times 2 times 1, and then we've got 2 times 1, which is 2 factorial. And then 5 minus 2 is 3, so we've got 3 factorials. We can cancel out those, and we get 10 possibilities. But why? So here's a smaller example that explains why this works. I have 3 friends, and I want 2 in the picture. I'm going to list all the possibilities. I'm just going to give them names so we can kind of draw this out. So I'm going to call them L, K, and B. And I'm just going to make a diagram that says, all right, I've got those who are in the picture and not in. So I could have L and K in and B out. But with B out, I could have K and L in. Now I have B and K in and L out, or K and B in and L out. And then, of course, I could have K out, L and B, or B and L. Now check this out. I have 6 arrangements, but I only have 3 if order doesn't matter, because the first 2 are really the same if order doesn't matter. And the third and fourth one are really the same if order doesn't matter. So let's look at our 2 arrangements, our 2 equations, and see how this works out. My permutations is order matters. So that's why it's 6, because they're different, L and K versus K and L. And my equation says it's 3 factorial over 3 minus 2 factorial. So it's just 3 times 2 times 1, which is 6. But if I don't care about order, then I have this extra thing on the denominator. So I'll have 3 factorial on the top, and now I've got this extra thing on the denominator, which cancels out my duplicate choices. So I'll have 2 times 1 times 1. So my answer here is only 3. I've canceled out my duplicate choices. So that is your World War intro. The bell is about to ring. I know that was fast, but I wanted to show you as quickly as I could counting methods.